I can just get started? Okay. Hi everyone, I'm Andrej Bauer. I'm glad to be here for 4 days. It's 1:40 a.m. for me. So I'll try not to fall asleep, and you try to do the same. So there will be 4 lectures, and I'll be talking about algebraic effects and handlers. And I would like to go through the general theory. And the lectures will go from math to programming, because today we're going to look at algebraic theories. And then tomorrow we're going to look at how to make a programming language out of this. But when we make the programming language, we'll forget about the equational part. So then the third lecture, I want to go back to equations and how you reason about such programs, and then at some applications, what kind of things you can do with algebraic effects and handlers. And so in a way, this is going to be the opposite of what Dan was telling you in the previous lecture when he said, well, you usually start with an operational semantics. But I think here we have a very fine example where even historically, first there was the notational semantics, and then there was operational semantics. So it's really going to be in this direction, where we start with math, and we get to programming. John Power and Gordon Plotkin were the first to propose and study computational effects as algebraic theories, and if you read their stuff, it's full of category theory, and it's just like lots and lots of math. And then later on, Mattia Pretner, who was a student of Gordon's, he also worked on this, and then he came back to Slovenia, and then we worked out a programming language out of all the theory. And so I'm going to go sort of vaguely in the same direction, so that you can see how mathematics can actually inform programming language design. So I think that's useful to see. If you have any questions, just ask me. Raise your hand. I ignore you. You say, hey, I have a question. Okay. If you don't ask any questions, I might ask you questions. We'll see. So let's start by reviewing some basic mathematics, namely algebraic theories. As I said, you could do this with lots of category theory, but I'm going to keep things very simple, and we're just going to use set theory, so just the basic setup, what I hope is going to be most familiar. But you should keep in mind that you can generalize this stuff to death. And then you actually need to generalize it when you want to put in other features into your programming language, like recursion and things like that. We'll discuss that. So let's just start with the basics. So the first thing we're going to look at are algebraic theories. And this is a well-studied subject. It also goes under the name of universal algebra. If you look at math books, it's called universal algebra. And let's start with an example. So I hope everybody here has had some math. Like, for instance, you should probably know what a group is, or somebody once told you what a group was, and you cannot deny it. You know, that's the minimum I would expect. So let's recall an example. A group is a what? Well, it's a structure. We have a set, G, and then we have an element, and we have 2 operations, multiplication and inverse, such that some theorems, some equations hold. And so what are the equations? The equations are u times x equals x times u, and maybe even before that, multiplication is associative. And then we have the inverse laws that x times x to the minus 1 is the unit, and the same on the other side. And it's not really important that I jotted down the definition of a group. The important thing is the form. I want to observe the form. So the form is that we have some operations. We say, hey, we have some operations on a set. And then we have some equations. Now, you might wonder in what sense the element u, so to be a little more precise, so this is going to be an element of G. This is a map from G plus G to G. And inverse goes from G to G. So you might wonder in what sense is a constant an operation, but it's a nullary operation, right? So multiplication is a binary operation because it takes 2 arguments, and inverse is a unary operation because it takes 1 argument, and by the same counting system, a constant is a nullary operation which takes 0 arguments, and we'll make this a little more precise. Yes, U is supposed to be, U is an element of G, right? So every group has an element that is neutral for multiplication. I could call it 1, maybe that would be some, if that makes it easier. It's operations and equations, and the operations are everywhere defined. They're not partial operations, they're everywhere defined. Now, it's possible to give the definition of a group in a different way, which is not like this. So, for instance, an alternative that you could see would be to have a monoid. So what's a monoid? A monoid would be something that just has a neutral element and a multiplication, but no inverses, right? Just like this, but without inverses, a monoid. Plus an axiom that says for every x, there exists a y such that x times y equals u equals y times x. Now, it turns out that this is equivalent to defining a group, because you can prove that if every x has such a y, that in fact this y needs to be unique, and then you call it the inverse. But that's a little theorem. You have to actually prove that this y, which is every x has a y, that it actually has in exactly 1 y, that it follows from the rest of the axioms. And what I'd like to point out is that there is a difference in form. It's defining the same kind of structure, but there is a difference in form. This is just operations and equations, whereas this one is operations and equations and an axiom which is not taking the form of an equation because it's for all exists. Whereas these guys here, you can read these the variables x and y as for all, for all, for all. But this one is for all exists. And that complicates matters. From a logical point of view, that makes it more complicated. And in general, having just equations gives you certain guarantees. It tells you that the models that you're going to have and that the theory that you have, that it has certain nice properties and that it will behave nicely and it's simple. So it's a good idea to try to stick to this form. And so that's what we're going to do. We're just now going to define what it means in general to have a theory which is like this. So operations plus equations. And there are lots of examples. A group is just one example. And so we're going to, let's write these things down. So if you look at how this works, there are really 2 parts. You first need to say what your operations are. And for each operation, you have to explain how many arguments it's taking. And after you set this up, then you can start writing down equations. But when you're writing down equations, well, you need to explain what's allowed to be on the left-hand side and the right-hand side of the equation. So these are some sort of terms or expressions, and so you need to explain what they are. So let's do that. So I'm going to define first what a signature is. Definition, a signature is just a collection of operations, operation names. So it's going to be a collection like this. op I and I for some indexing set I. So any number of operations, doesn't have to be finite, okay? Where each of these op i's are, we call them the operation symbols. So usually they're syntax. Usually they'll like there's the symbol plus and the symbol times. But formally speaking, they don't have to be symbols. They can be just anything. Yes? And each of these ni's is a natural number, is the arity. We call it the arity of the operation symbol op I. I'll try to be exact and always call it an operation symbol when I have in mind the description of a theory. And then we'll call it an operation when you have a specific group or specific structure in mind. So this is just the first piece of data. This is what you would get here in this line. Okay? It's just saying we have some operations. Notice that I did not mention any sets. See, this is the carrier set. It's not there. I don't need it. It's implicitly there, okay? We'll see later how it comes up. So I just need to explain the shapes of these operations. Now, once I tell you what operations are available, and I tell you there are arities, then I can explain what it means to build one of these expressions. So let's do the next thing, is a term in context x1, I'll explain this, xn is, so we are going to look at how to build expressions, but when you build expressions, you have to know what variables are allowed. It's very important that you first say what the variables are, what are the possible variables that you can mention, and then you explain what the terms are. There are reasons why I want to do it this way. So, and this is so a term is, there are two possibilities. It's either one of the variables. It's one of the variables xi, or it's one of the operations applied to some terms, t1 to tni, where the t1 to tni are terms in the same context, in context x1 up to x. So let's, just because we have ends, just because I have ends here, okay? So not to mix things up, let me make this number of variables k, because otherwise there are too many ends, okay? So we have k variables. Questions? And this is meant to be read as an inductive definition. Yes?
I do not understand how for all x there exists y is removed by having a.
Sorry?
So you said these both are equivalent.
Yes, so what I claim is that, first of all, if you have a group, then it is also a monoid with this property. Okay, that's the easy direction.
What's the implication of saying this, and what's the reason behind it you could say that group and this is?
Sorry?
What's the intuition?
Well, you can actually, actually it's not a complicated proof. So let me tell you the proof, and then you'll tell me what the intuition is. Okay, here's the proof. If I have a group, then first, because you just forget the inverse and you click on it, okay? And now, if I have a group, is this true? That for every x there exists a y with this property? And the answer is yes. Namely, take y to be equal to x to the minus 1. And then it has this property. So every group has this property. Now, the more complicated direction is this. If I have a monoid with this property, then it is a group. And in exactly one possible way. And what you do is, so this needs a little bit of proof, and I'm not going to go into it. First, you prove a lemma, which says if x times y equals, so you prove that this y is unique. So you prove lemma if x times y equals the unit equals y times x, and x times z equals u equals z times x, then y equals z. Okay? So what this says is, this says every element has an inverse. But this lemma tells you that if there is an inverse, there's at most one. So if you assume that everybody has an inverse, that means everybody has the inverse. And so now you have no choice as to how to define the inverse. The inverse, we see, because we have a monoid, but we're still missing the inverse operation. And so what we do is we define the inverse operation. The inverse operation is the inverse of x is the unique y, which makes this true. Okay? And so then you see that it's equivalent. And this is a little play that you play in algebra, and it's good to know because it's, sometimes you want to know that something is a group, and you have this much structure, and then you just need that. Yes? So it's good to know. But from the logical point of view, from the formal point of view, this is the desirable formulation. Did I answer your question? Okay. This should be read as inductive definition. Which means I'm giving you ways of constructing terms, and these are all the ways of constructing them. So that's what a signature is and what a term is, and then what is a theory? Definition, an algebraic theory, sometimes also called equational theory. So a related context is a Lavoisier theory, but it's not quite the same, so let's not call this that, but it's theory. T is given by, well, a pair of things, a signature and a set of equations, where sigma t is a signature, and ET is a set of equations. And what's an equation? An equation is given like this. You give a context, and then you give two terms. So where L and R are sigma t terms in context, in the given context. So if we go back here, we're going to see that it's kind of that, except that I needlessly put this G down here because I'm not really using it. So if I formulated the theory of a group as my example, the theory of a group, what is it? So let's be quite formal here, okay? So the theory of a group would be like this. The signature, sigma group, it has to have three operations, yes? So u comma 0, because it has signature, so it's a operation symbol, and then it's an arity. Now, I don't want to use these fancy mathematical symbols here. Okay? If I want to adhere to this kind of syntax, now I have to rename these ones. So I'll call them um for multiplication, and it's binary, and I for inverse, and it's unary. And then when we write down the equations, now lots of things become forbidden because we're being very formalistic. For instance, it's not, yes?
I didn't get them in U0, M2, and 0 to 1. What are these?
So again, these are the arities. If you look here, I said when I give a signature, I give a bunch of operation symbols, and for each one of them, I give a natural number. And this natural number, ni, is telling you down here, see, ni? It's telling you that the operation, the operation op I, it wants ni arguments. Yes? So that's what the arity is. The arity tells you how many arguments it wants. Yes? So what I'm saying here is, U takes 0 arguments, N takes 2 arguments, I takes 1 argument. And now if you want to write down the equations, let's write down some of them, maybe not all of them. Okay, so one of them would be that x in the context x. Okay, so let me write here, let me introduce quickly a notation. So, oh no, it's like I have it here, okay? So this notation, so in the context x, okay, let's do the first one. M U x equals x. That would be the first equation. So another one, let's do one that has let's do one of the inverses. So in the context, it doesn't matter what I call these variables. It could be y. M x inverse of x equals u applied to 0 arguments. Yes? So now, if I'm very formalistic, when I have a constant, I have to apply it to 0 arguments. I used y, yes, if that serves me. It's more economical to just change this y to x. There we go. Okay, is it clear how this formalism is going to work? Okay, now you can give lots and lots of examples. From mathematics, you open your algebra book and you look at them, and some of them are going to be in this form. For instance, a ring is going to be in this form. So a ring is going to be like this with much more stuff because it's going to have a 0 and a 1 and a plus and a minus and a multiplication. So let's see what would be some other, let me write down some other examples. Okay, so ring, sure. Now if you don't know what a ring is, you can look it up, it doesn't matter. So one possibility is the empty theory. So the empty theory doesn't have any operations, it doesn't have any equations. It's a theory. Okay? So another one, we're doing maths, yes? So the mathematics is the science of studying pathological examples, yes? So we should definitely include the empty theory. Another one that we want, let me properly write down 2 of them. I will not always adhere to this formalism, okay? I'm not a computer, okay? So I will use mathematical notation. So here's an example. The theory of a pointed set. It has the signature. It has one constant, the point, which I will use a bullet for, and there are no equations. So you just say there's a constant, call it the bullet or something, and nothing else. Okay, here's one that's not completely crazy. Example, this one we will actually want to know, semi-lattice. So the semi-lattice would say, now the signature would say, we have one element which we call bottom, and it's a constant, and we have one operation which I will call join, and I'll write it like this, and it's a binary operation. And what are the axioms? Here are the axioms. First of all, well, let's say, so first of all, the bottom is the neutral element. The operation is associative. And commutative. And idempotent. That's one example of a theory. It'll come up later, so that's why I want to do it now. Now, how about something like a field? Now, what is a field? A field is like the sort of thing you get for complex numbers and real numbers. So a field would have plus, minus, times, but it would also have to the minus 1, and it has to have a 0 and the 1. And if you look at the axioms for a field, then something happens. The minus 1, this one here, is problematic. And the problem is that it's not everywhere defined. The inverse of 0 is undefined. And you could try to fix this, but if you try to fix it by some arbitrary means, like the inverse of 0 is 0, or the inverse of 0 is 42, or anything like that, you get into trouble. You break things. So at face value, the theory of a field, which means you support these operations, and then you write down the equations that you would imagine need to hold. So, commutative, this needs to be the inverse operation to that. Commutative, associative, distributivity of plus and x and neutral elements, la la la. You open a book, you look at what is a field, and then you'll get the axioms, and there's the inverse operation is not total. And so at least the way that the theory of a field is usually given, it's not algebraic, because operations must be total. It have to be defined everywhere, and this one is not defined everywhere, the way that fields are usually given. Of course, we don't know. Maybe there is an equivalent formulation of fields which is algebraic. We don't know yet, because, here, look, you start with this theory and you say, well, it's not algebraic. Yeah, but if you think a little bit, you can find an equivalent algebraic formulation. So maybe fields are algebraic. We'll see later that they're not, but in principle, we don't know that yet. Okay, so now that we have the idea of what is the theory, let's talk about interpretations and models. So far, I described a piece of formalism, a language that allows me to speak about algebraic. I can describe algebraic structures. I can just put down the axioms. So when I put down the axioms for a group, like there, they're missing. So this is just a piece of formalism. And that should not be confused with a particular group. If I define a particular group and I say Z3 is the group whose carrier is the element 0, 1, 2, here's the multiplication table, that's an example of one group. So there is a thing called the axioms for a group, or the theory of a group, and then there will be lots of examples of the theory. So let's make that precise. Oh, I forgot to say, and I better say it now, on the GitHub repo for the school, I put in a repository where these lectures are summarized, and the reading material is there. And in particular, I wrote up 25 pages for this lecture. Actually, I wrote it up for other reasons as well, not just for this. It's called What is Algebraic About Algebraic Effects and Handlers. And so I recommend maybe that you look at this, because it has more examples and more of everything. And there are problems at the GitHub repo. There are problem sets. There are lots of problems for each lecture, many more than I would expect any human to actually solve. But let's make a deal. Pick at least one and attack it, okay? And they go from easier/less work to harder/more work. Like today, the last one is formalize the theory of algebraic theories. That's not something you will not do that before dinner. Yes, so let's define interpretations and models. And this is going to be an example of the notational semantics. So we're starting with denotational semantics. We have a language, namely the language of algebraic theories. It's very simple. You can just make these terms. Okay? There's no while loops and recursion and crazy stuff, no types, nothing. And we want to give a meaning to them. So here's how we're going to do this. I get what? I get three whiteboards, but I can only show 2 at a time, right? Okay. So this is now 2 interpretations and models. By the way, if you ever took a course in logic and first-order model theory, first order logic and model theory, you will recognize that all of what I'm doing is just a special case of that. I'm just using a small chunk of first-order logic. I was told to replace these every once in a while, so maybe now is a good time. So suppose we have a theory T. When I say theory, I always mean algebraic theory. And then an interpretation I of T is given by, where's the middle? Around here. Is given by a carrier set, which I will write like this. Okay? The carrier set, I, has the carrier set, which is like the absolute value of I. And for each operation, so if I have an operation I of arity Ni in the signature of T, a map, which I will write using the semantic bracket, op I. And since we're going to have more, sometimes you will have many interpretations running around at the same time, I will subscript it here with I. Okay, so this is with respect to I. And this is going to be now a map on the carrier where this needs to be of the correct arity. Yeah? That's what an interpretation of, oh, sorry, I was going too fast. This is an interpretation of the signature of the theory. Okay? So far, I haven't done anything with equations. So if I have an interpretation just of the signature part, all you have to do is you have to say, okay, we're going to have a set, and then we're going to have a bunch of maps on the set. But so far, I'm not requiring that they satisfy any equations. I'm just giving you the basic raw data. Yes?
What exactly is signature here?
Signature is up there. So a signature
Is operation and
yes, a signature is just a collection of data, and it's just a bunch of operation symbols together with their arities, nothing else. Okay? Yes?
The carrier set is in the meta domain.
It's a set. So what I'm actually describing is what is an interpretation in the category of sets. But you can see that this would work, say, also in some other domain. So for instance, this could be a topological space, and these would be continuous maps, or anything like that.
Why we put the bars around the line?
Sorry?
Why you put the bars around the line?
Oh, just to have a notation. I need some way of saying every interpretation has a carrier set, and I need a notation for this carrier set. Okay, that's the only reason is that if this was coq, I would say something like carrier I or something, and then I would make an implicit coercion, and then I would write I. Yes. Clear? Okay. So, such an interpretation, what do we want to say next? We want to say, okay, you told me how to interpret the operations, but now you also have to satisfy the axioms. So I want to say, and the axioms are satisfied, are validated by this. But in order to say that, I need to extend this to terms. So the next step is, we're not there yet. I cannot yet say what it means that the axioms are satisfied. So now I also say each term. So if I have a term in a context, let me write it like this. If I have a term, and so this is a term in this theory, of course, is interpreted as a map, so I'll write the semantic bracket here as well. And this is going to be, and now in order not to go crazy, let me write this thing as I to the ni, okay? So in general, x to the m is just an m-fold product of x's. And here's the trick question. What is x to the 0? Yes, but we need a good notation for it. So x to the m is the set of all the m tuples, yes? So x to the 0 is the set of all the 0 tuples, but there is just exactly one 0 tuple, and here it is. So that's how, and we will also write this to be 1. Okay. So now you know why in ML they write it like this, because it's a 0 tuple. So this goes from the carrier to the k, because I have k variables, to I. And this works like this, as follows. And so now I use recursion because terms are defined inductively. I can now define a function on them recursively. So I have to consider two cases. What happens with variables and what happens with these compound terms. And when I define the compound terms, I can already presume that I have defined the meaning for the subterms. So my semantics is compositional because the meaning of a term is defined as a function of the meaning of the subterms. So the variable, how do we interpret the xi variable? What is this? Well, this needs to be a map which goes from I to the k to the I. Well, it's the map, it's the ith projection. So this is just going to be pi I, the ith projection. So it takes a k tuple and it gives you the ith component. And what is the meaning of x1, xk of some t1 up to tni? So you could, at this point, write some sort of syntactic craziness, but let's try to do it with compositions of functions, okay? So let's start where we are supposed to start. We're supposed to start here, and we're supposed to start here and supposed to land there, okay? So it's going to be start with I to the k. And now each of these guys here is also a term in the same context. So we can interpret those, and each one of them will give me, if I interpret T1, and now I will allow myself an abbreviation. I will write like this. Oh, there, we need I everywhere. If I interpret T1 in the same context, I didn't write down the context, so there's a context missing here. Okay? Yeah? So if I write this one down, I will land where? I will land in I. Yeah? Because this is just interpreting the first one. Okay, what if and then I interpret the second one and the third one and all of them. And so then I get here the interpretation of all of them. And I can tuple those together, and then I won't get just one of them, I'll get ni of them. But then I can take my op I, which wants ni of them, and it'll give me the I. So here I put op I, and then I'll line in I, and it's this composition. So it's just the composition of the meaning of the subterms composed with the meaning of the operation. And this formulation, of course, is going to work in other categories, in case you worry about other categories. So what do we actually need for? We just need finite products. Right? So if you know about categories, as soon as I have finite products, I can do all of this stuff. Yes?
You presume that you know the arrays of the
Tisa-bis are terms, they're not operations. So you can't really say what are their arities, but what you should ask is in what context are they? What variables can they use? And here we defined that a term in context x1 up to xk is of this form, provided all these guys are terms in the same context. So yes, so when you have terms in context, the subterms have to be in the same context. This is a very simple language without any binders. When you have lambda calculus and you start binding variables, then the context can change. But we are in a very simple position. You just give yourself some variables. All the subterms can use just those variables and no others. Does that answer the question? So now that we know how to interpret terms, now we can somehow get to that third. Ooh, there's 4 of them, or what? There's actually 4 of them, right? So now a model definition, and I was told to switch these every once in a while. A T model is an interpretation, let's call it M, of theory T, so that for every equation x1 up to xk L equals R in the equations of T, the maps. So now I can take the left, this is a term in this context, so therefore I can interpret it, and I will get a map like that. And I can do the same thing with the right-hand side. And what does it mean for this equation to be valid? Well, these two maps are equal. The left-hand side and the right-hand side define the same map. That's just what it means, that the equation holds. Clear? Any questions? In the written notes, at this point, I think I go slowly through some of the examples that I'm not going to cover right now, but you can have a look at them, and I actually laboriously go through like the interpretation of something or other, just to see how this really works. For instance, now you should convince yourself that if you take the theory of a group, and then you work through this, and you say, what is a model of the theory of a group? You should get the usual definition of what is of a group. It shouldn't be something strange. It should be just a group. So maybe we can have, let's have some examples. Let's have the silly examples. The theory of a pointed set. A model of the theory of a pointed set. Yes?
So you have the two maps being equal.
Yes?
But if you generalize this to other categories,
Okay, so the question is what happens if you go to some other category? So if you go to some other category, this will be a morphism and it will be a morphism, and then it will just say equal morphisms in that category. So if you're interested in some notion of equality, make sure that your category has that notion of equality of morphisms, and then you'll be fine. So what is a model of a theory of a pointed set? So what was the theory of a pointed set? It just had one constant and no equations, so that's going to be really simple, okay? Because there are no equations, we can forget about this last part. And so what you need to do is, so it's given by what? Well, a carrier set. Let me call it now. So a model, let me call it M. So a model M of, so a carrier set like this, and a map that interprets the bullet, and the bullet has to go from M to the 0 to M. But now let's simplify this a little bit because it just looks ridiculous. So this thing here is like a map from 1 to M, but maps to from 1 to M are in bijective correspondence with the elements of M. So I could say isomorphically, normal people, the way they would say this is just some set, and they wouldn't even write this business with bracket M and so on. They would just say it's a set S, and it's some element S. S is a set, and S is an element of S. So let's see, why is that? Well, this S is just that set, okay? So it's the carrier. And how does this S correspond to this map? Well, it's just this idea that if you have a map from 1 to M, that's picking out exactly one element. So I hope this is familiar. Yes? No. Yes. I actually, you will not believe me this, but I did not actually pay Dan anything for the following, to ask the question, because my next example is every theory T has the trivial model, which is the carrier set is 1. And all the operations, any kind of operation that you have, it's interpreted by the only possible map you can have from 1 to the n to the 1 to n. And all equations hold because all maps into 1 are equal because it's a determinal object. So you always have this model. Is this a good thing or a bad thing? It's a good thing. So the next time you speak to anybody who does algebra and they try to convince you that when you have a ring, 0 has to be different from 1, okay, tell them this is totally wrong. Because if that's what you require, you have now lost the form. It's not an algebraic theory anymore. So if you exclude the trivial ring from your rings, you will have destroyed the algebraic structure of rings. So how can you call yourself an algebraist? Okay. What do you call yourself? Sorry, what?
You're saying a ring's no longer a theory.
It's not an algebraic theory. Right. If you add the axiom 0 is not equal to 1.
If your definition of includes this,
yes,
that every theory has the trivial model.
Right. So we're really discussing whether we should allow this. And my answer is yes, of course. Because otherwise the category of models will lose good properties. So that's a pragmatic reason. Here's a yes. I like it how you're most interested in this example.
So if we're
Right, exactly. So you have found the reason why you cannot fix fields because unless you allow 0 equals 1 to be a field. How do you feel about that? Yes?
No, I was giving
Oh, you're giving a thumb up? Okay, so he's happy. Now we get to you. Okay, so suppose we allow the trivial field. Did we fix it? Is it now algebraic? Something to think about. Was there another question? Okay. So let me give you a hint. Here's another example that's worth knowing. Still don't have to delete anything. Product of models. Let me just do product of 2 models, but I can do product, it's possible to do a product of any number of models, or it's also infinite number. So if M and L are T models, define the product model to be the following. M cross L is just the Cartesian product. So you just take the Cartesian product and you do all the operations component-wise. So how do we interpret op I in M cross L? Well, this is going to be a map from M plus L to N to the I to M cross L. How does it work? It works component-wise. So here, best way to write it, op I in M cross L of some tuple of things. So here's a tuple of things, A1 up to AN I. Going to be, so I have to give a pair, and so I say, okay, it's op I in M of the first projections and it's op. It looks all very complicated. It's better not to read what I'm writing. It's better not to read what I'm writing. It's better to just listen. You take the product of the carrier sets and you do all the operations component-wise. Why are equations going to hold? They will hold component-wise. Does it matter how many components you have? Nope. Now, let's get back to the question. Who was the person? What? Something missing? Sorry?
The product of the models, you can actually call that a model, right?
It is a model, yes. Models have products.
So trivially, because you can put pairs, you can make pairs of pairs. So
Yeah. No, but you can make infinitely many if you want to. Yeah. Why is the theory of fields not algebraic? Is there a field of size 2? Z2. If you have numbers modulo n, when do they form a field? When n is prime. Okay, so we have Z2, which is a field. We have Z3, it's a field. Therefore, Z2 times Z3 must be a field. Is it? Nope. End of discussion. It's not algebraic. So far, we have been doing interpretations of models. Let's see, how far do I want to get today? Okay, let's discuss the next thing. And the next thing is that among all the models, some of them are more important than others. So I know that this one interests you a lot, but this one is not the most important one. The most important one is the free model. So let's discuss what a free model is. I wonder if I have an empty whiteboard somewhere. I probably do. This one might be empty, but it'll be difficult to put the free models here. But let's try. Number 3. Free models. So suppose you have a given theory T and a set X. The free, no, actually let me first describe what it means for a model to be free. Say that a T model M is free over X, or freely generated by X is better. Freely, a T model M together with a map eta from X to M, the carrier of M. So a T model together with such a map is freely generated by X when the following holds. It has a universal property. I'm secretly doing category theory here. So when what? So here's what I have so far. I have a set, I have a model, and I know how to put this set inside this model. And I want to say that this is the best way of doing it. And so when you want to say that it's the best way of doing it, what you need to say is it's better than any other way of doing it. And then it's the best way. Okay? Now, when you say that it's better than any other way of doing it, that means we say, okay, suppose we had another way. So here I have some other model. Then I want to say this way is better than that way. And the way you do that in category theory, how do you compare things? Well, you compare things with you compare things with this, right? This is how you compare things, yes? But in category theory, you don't compare like this. You compare with arrows. So what you want to say is, you want to say this one, if I did this naively, I would say this one is smaller than that one, because it's the best. It's the most economical one. So instead, I say it's the best, which means there is an arrow going here. And moreover, I require that it's unique. It's so good that there is just one arrow going this way. And this arrow needs to be a homomorphism. I forgot to define homomorphisms, you see? So we say that, like this. Okay, so the best way, M is freely generated by X, by definition, if there is some way of putting X in, so together this eta is a data to freeness. So M together with this eta is a free model generated by X. If any other way of putting X inside gives us a unique homomorphism from here to there. So what is a homomorphism? I'm running out of whiteboards. Well, this one is content-free. I can get rid of this one. I should get into the habit of switching pens anytime I delete anything. A T homomorphism F from M to L. Can you guess what this would be? So what is a homomorphism in algebra? A homomorphism is a map that preserves the operations, that commutes with the operations. So that's what we need to write down. For every operation I in the theory T, we have, if I apply F to, now we have to be a little bit careful. So these are models. So if I apply it to op I in M, and then here I just have some arbitrary elements, A1 up to ANI. Okay. This equals, I can switch around the operation in F. So, but now this is going to be in L of, and here I have F up to F ANI. All I wrote is I can exchange the homomorphism and the operations. Yes. Now, why would this be important? This is going to be very important for us when we get to computational effects. Yes?
What exactly is freely generated? How can something...
We say that M is freely generated by X. So terminology is going to be that this M together with this map is, well, people say different things. Free model over X, or free model generated X, or things like that, okay? Different things. They say different things. This pen is not good. Let's do an example. It's general category theoretic fact that when you have universal properties like this, it actually turns out that if you have two such freely generated things, they will be isomorphic in a unique way. So that's something you should convince yourself, or ask somebody who you think knows category theory, and then they won't be able to say, no, I don't know category theory, and they'll have to prove it. But I'm not going to get into that, but if there is a free model, it's unique up to isomorphism. So let's have an example. So let's calculate, let's show that there is a free model of the theory of a semi-lattice. Let's define a model. So I'll write it like this: P less than omega of X. Let this be all subsets of X which are finite. Finite subsets of X, okay? And so now the claim is that if I take this, the finite power set of X, together with the empty set and union as the operations, is the free semi-lattice generated by X. So my first question is, why should you now complain that I did something wrong? I think I said it many times that when you have a free model generated by X, you should not give me just the model. You have to give me the embedding of X. You have to tell me how X goes inside the model. So I forgot to tell you that. So with eta from X to E omega of X, given by eta takes X to the singleton X. So let's do this mentally, okay? Is this a semi-lattice? Is this operation commutative? Yes. Is it associative? Yes. Is it idempotent? Okay. Is this the neutral element for the union? Yes. So this is a semi-lattice. Okay. That much is good. And so now we stare at this definition here and we say, okay, so I have X. Here I embed by singleton into this. And then I give myself some other semi-lattice, which has bottom and join. And now I wonder, given such an F, what is this going to do, this thing here? So this thing here has to be a homomorphism. So it has to preserve the operations. So first of all, because it has to preserve the operations, it has to map the empty set to the bottom element, yes? Because that's what it means to preserve operations. It also has to have the property that it preserves union. So if I have S1 union S2, this needs to be F of S1 join F of S2. But what does it mean that this triangle commutes? I never said commute. It means this composition equals that composition. So this one says that F bar of singleton little x equals F of x. And so I wrote down the first and the second condition say that F bar. The third one says that this diagram commutes. And now I stare at this and I say, is there such an F bar? And if there is such an F bar, is there 2 of them or 17 of them? How many are there? And so I'll leave you to think that, to see whether this F exists. Okay, something to think about. It exists and it's unique. Yes?
So why the singleton? Why did we give eta twice?
I gave eta twice. No, I didn't give eta twice. First, I gave the type of eta, and then I gave its definition. I see you are a Haskell programmer, so let me help you. Better? Yeah? Okay. Yes. Now, we have one example of a free theory. Does every algebraic theory have a free model? Yes. Every algebraic theory has every model generated by any set. So this is important to know, and it's important to understand what these models look like, because they will give us an intuition about computations. They will give us something called computation trees. So let me spend a little bit of time on that. Where do you suggest I go next? I am, right? I have to delete something. Yes, Dan?
Maybe I'm anticipating this question, but here you showed how you kind of guessed the free model.
I guessed the free model. Yes, in this. Yes. I will now describe the general construction of free model. So, how would you prove that every theory has free models? Well, by direct or indirect means. We're computer scientists, so let's do direct means. Let's just have an explicit description of what it is. Before I just jot it down, let's think a little bit about how this might work. This free model here, this thing here, you see, it has to be the most economical one, because it needs to go inside of every other model. So it needs to be as small as possible so that you can put it anywhere else. But there is a trick. When I say small as possible, I don't mean as few elements as possible, because if that were the answer, we would use the trivial model all the time. So why can't we use the trivial model here? Well, homomorphisms must preserve equations. The trivial model believes in all equations. And so that's what the problem is. So what you need, when you say smallest, you need to say smallest in terms of elements that need to be there, as well as in terms of what equations hold. The free model has to be the thing which is built in the most economic way possible with respect to the elements that are there, as well as with respect to the equations that hold. We have to put in as few elements as possible and make as few equations hold as possible. Then we win. If we make too many equations hold, that corresponds to bunching together elements that we should not bunch together. So that's the idea. So we're going to do this in 2 steps. We're first going to make candidates for all the possible elements. And then we're going to quotient them by as few equations as needed to get a model. So free model construction. This one is bad. I will call it like this, free TX. And I'll do it in 2 steps. I don't know. Okay, this one's better. So step 1, first we construct a thing called tree TX. And this is the set of well-founded trees. And I have to explain what these trees are. The word well-founded, when it refers to trees, always means no infinite paths. It means every path is finite. So these are trees which are inductively defined, like this. So now I'm throwing in elements. So I ask myself, which elements must necessarily be there in the free model? Well, let me tell you that for every x here, we necessarily must have something there. Otherwise, we will never get this map eta. So what we say is, for every x in x, and now I want to say there is a tree which is like a leaf. It's an endpoint, it's a leaf. It doesn't have any subtrees. It's just a leaf labeled with x. So now I need a labeling. And Dan had the same problem because he had the in left and in right, and he tried to avoid it. Yes? If I were a sloppy mathematician, I would just say x is a tree. But I'm not a sloppy mathematician. And I need to label it. And now it's very important that you understand that this label is completely arbitrary. It doesn't matter whether I call it in left or in right or leaf or whatever. So I'm going to call it something that's going to be beneficial to me tomorrow. I'll call it return x for mysterious reasons. And so here's another thing that must necessarily be there. Because I'm constructing a model, I need to give the interpretations of the operations. So there needs to be a way of building new trees using the operations. So if op I ni is one of the operations, and I have trees t1 up to tni, then I have a tree, and now I need notation for the tree. But I will draw it, and then I'll give you the notation. So the drawing is this. I have the root of the tree, which is labeled by op I, and then it has ni subtrees. And so here I have my subtrees, t1 up to tni. Why do I need to label this? Well, because maybe I have 2 binary operations. And then I need to know whether the two trees growing up, whether they're supposed to be added or multiplied or what. I need to label it. And so now I need a notation for this, and I'm going to use this notation. But this is a purely symbolic notation. What I really mean is this tree, and now I need a notation. And so I could invent some slightly more complicated notation, but I'm not going to. So think of this as the tree, this tree here. So that's the first step. We should finish up. So that's the first step. And the second step, which I have to put somewhere else, but probably not too far away, is to, so right now, the problem that I'm going to face, so am I done? Why am I not done? I'm not done because there are equations. And for instance, if there is an equation that says that I have a binary operation which is commutative, well, then the tree, which is like this or like that, if I exchange the two subtrees, that should be the same element because commutativity requires that they're equal. So because they are equations, I now have, so to speak, the right elements. This was the most economic way of putting in the elements because I put in just the stuff that I needed. But some of them may actually, maybe some of them have to be considered equal. And so I need an equivalence relation, and then I will quotient by that equivalence relation, and that will give me the correct answer. So, I don't know. Sorry, say again?
The very last thing you mean, this is an element of tree.
Yes, it's an element of 3x, 3tx. You should, if you know Koch or Agda or Lean or Haskell or ML, but not if you know scheme, then don't listen. So then you should think about what this is in terms of types. So actually you can tell me, what is this in terms of types? What am I defining? Am I? Yeah, type inference, yeah. It's a more general concept than that. It's like the type of ASTs, of abstract syntax trees, with one proviso. You have arbitrary, you see, these are the variables. You can just have any set of variables. You maybe have infinite set of variables. So I would say it's an inductive type, right? Okay, so here's the reverse question. Can you think of an inductive type which isn't like this? And the answer should be yes, you can think of it, but, or maybe not, I don't know. It depends on what you understand by the words inductive type. Right? If you take a sufficiently narrow view of what is an inductive type, every inductive type is just a bunch of trees. No, that's, well, after the equivalence relation maybe, yeah. So, but we also need an equivalence relation, so let's wrap up for today. So we define an equivalence relation, so some operation T on 3x, oops, keep doing this, 3tx, to be what? Now, when you define an equivalence relation, there is a very nice thing. I can give you any relation and say the least equivalence relation generated by it. So whenever I write down some conditions that I wish on an equivalence relation, then I can say, take the least such. So to be the least equivalence relation such that, so I'm really throwing in equations. Which equations should I throw in? Well, I should throw in the equations of the theory, yeah? Okay, so I have to write that somehow. Any others? Yes, there are others. I need to make this relation a congruence relation. Now people, when people say congruence, so it took me forever. I think like at university, like, I don't know, I was the fourth year. I finally realized what was the difference between an equivalence relation and the congruence, because they all seem to be the same thing. What is the difference? Well, an equivalence relation is just an equivalence relation. A congruence is an equivalence relation which commutes with operations, right? If there are some operations flying around, then you call an equation, an equivalence relation a congruence if it's an equivalence relation, and in addition, it behaves nicely with respect to the operations. So the first condition is that, okay, I will not do this today. I will leave this, okay, here. I have a trick up. So this is homework. But I will tell you exactly what the homework is. So you need to write down these two conditions. So as PhD students, you have to learn the art of reconstructing what the guy meant. Yes? So this is an important art. So here's something for you to practice. So it's a congruence. With respect to forming trees. And it validates the equations of the theory. So I'm going to tell you the best trick to find out what the guy meant. You find the reference and you read it. The guy thing. So you find it in here and you find, okay? So, yes, question?
When we say we validate the equation, does that mean we take our new equivalence and we put it where the equal sign was in the original equation?
So, vaguely speaking, that's exactly what you do. You take your equations and you replace the equal sign with the wiggle.
Yeah.
But then you have to ask yourself the thing that my advisor always asked me. What does it mean? Because you have a term, and then you have a wiggle, and then you have a term. You're not supposed to have that. You're supposed to have a tree and the wiggle and a tree. So something's going on. Yes? But, so I would say spend 10 minutes thinking about this, and after 10 minutes you look. If you look first, it'll be more difficult to understand it. If you, okay, so I'm going to wrap up. Let me just tell you where this is going, because I was just doing pure mathematics and maybe you are growing impatient. Tomorrow, we're going to generalize this a little bit, and then we're going to just change notation. I will not change any theory. I will not do anything. I will just write things differently. And it will become a programming language with computational effects. That's my plan. So we're going to get from here, there will be an uninterrupted line from here to a programming language with computational effects. Thank you.